Greetings, physics fans. Welcome back. This is going to be a new lesson here on forces. This is our next chapter. This is going to be the first lesson in chapter 4, and it's actually changing topics quite a bit. The last few lessons and chapters have been on kinematics, and we are starting on dynamics now. Dynamics explains why things move. We just were studying the motion beforehand and projectiles and all that type of stuff. Now we're going to study why things move. So grab the notes or just watch as I highlight as we go along. And whenever we start a new chapter, and especially a whole new topic, we need to learn some terminology so that we can talk about it. So here comes the highlighter. The tendency of objects to resist their state of motion is called inertia. That is actually a definition. That whole line is the definition. Start off with a nice definition. The definition of inertia. The object to resist changes in their state of motion. Inertia is measured quantitatively by the object's mass. Objects will undergo changes in motion only in the presence of a net unbalanced force. So, anything with lots of weight, lots of mass, will resist changes in motion. And the heavier it is, the harder it is to change its motion. And it's only because of its mass. So inertia is kind of like mass. The more mass it has, the more inertia it has. An object that's at rest and it's very heavy is still very hard to get moving. It resists changes in its motion. Okay, and then you have to have a net force, an unbalanced force acting on it. Okay, whenever one object exerts a force on a second object, so there's two objects here, one object and a second object. When one exerts a force on this, the second object exerts an equal and opposite force on the first. So there's a reflex force on it. This is because a force is defined as the interaction between two objects. Ooh, there's another definition right there. Force is defined as the interaction between two objects. In the metric system, forces are measured in the unit called newtons. There's a unit there. And forces only occur in pairs. Ooh, important. They only occur in pairs. And one is called the action, and the other is called the reaction. So there's an action force, and then there's a reaction force. They occur in pairs, both of which constitute the interaction between one thing and another. Neither force exists without the other. Since action and reaction forces act on different objects because there's one that's causing the action force, then the reaction is the back one. Okay, and just notice the action's on this guy and the reaction is being acted upon that guy. So the two forces occur, but they're on different objects. Action and reaction forces can never cancel each other out because they can't add up because they're on separate objects. Interesting. Okay. Whenever you speak of a net force, you're speaking about all the forces acting on one unique object. Whenever you're talking about a net force, it's the forces acting on one object. And these forces are often summarized in a free body diagram. If the forces cancel each other out, then the net force acting on the body is equal to 0. So, first of all, the free body diagram, we're not going to do too much on that right away. That's about 3 lessons away till we start learning how to draw all these diagrams. And if the forces cancel each other out, then the net force acting on the body is equal 0. When this happens, the object is to be in a state of equilibrium. So if all the forces add up to 0, so we have F1 plus F2 plus F3, all these forces, if they add up to 0, then the object is in equilibrium. What happens if it's unbalanced? All this was when it's 0. What happens when it's unbalanced? When it's unbalanced, the net unbalanced force is upon an object. The object will accelerate. So it is not at rest, and it is not at constant velocity, but it will accelerate. Acceleration is not 0. The acceleration is proportional to the unbalanced force and inversely proportional to the object's mass. I'm going to do this one in green because some people will want to have that memorized, but definitely, this is math speak. You don't need to have this, especially the word inversely proportional, blah, 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 blah. And symbolically, this is written as A is proportional to F divided by M. That's what it means. Proportional to the unbalanced force and inversely, meaning M's in the denominator. Acceleration is always in the direction of the net unbalanced force. That's important. The direction of this acceleration is in the direction of the net unbalanced force. And a net unbalanced force of 1 Newton will equal or result in a 1 kilogram of mass experiencing an acceleration of 1 meter per second squared. So 1 Newton is equal to 1 kilogram accelerating at 1 meter per second squared. Okay. Okay, there we go. Let's scroll down a tiny bit. Now, when an object falls in a vacuum, the net force is simply the object's weight, and the object is said to be in a state of free fall. So this is what a free fall is. Free fall is something like a box or something that you dropped out of an airplane, and it's falling due to gravity. The force is gravity pulling it down. And there's no air friction, it's in a vacuum here. And it will accelerate at g, where g denotes the acceleration due to gravity, and near the surface of the Earth, it's 9.8 meters per second squared. We've been doing that. This is now just saying this is what happens with forces in mind. When objects fall through the air, though, in air, not through a vacuum, the net force is equal to the weight minus the force of friction. So there is a force of friction pulling up, resisting it, pulling up on it. Gravity's pulling down, and friction is trying to slow it down by pushing up on it. If we want, we're pulling up on it, however you want. And so the acceleration is going to be less than 9.8, less than g. And if and when the force of air resistance equals, so if this ever equals this, then that plus that, opposite direction, same length, same strength of force, it will then not accelerate. So acceleration terminates. And this is called the terminal velocity. Let's just take a quick peek of a little tutorial here. Okay, we've seen this projectile thingy before, but we'll just show you now. I'll put on air friction. There's going to be a drag force in here, and I'm going to overdo the drag force. I'm going to make the object very big, very light, with very dense atmosphere, so it will have a lot of drag. So we'll fire it here and we'll take a look what happens. So on your mark, I'm going to slow it down. Okay, so it's been fired off, and because it was moving really fast, there's a drag force, the force of drag here, the air frictional force. And there's a force of gravity always pulling down. You'll see that this force doesn't change because gravity is always pulling straight down on this object. So we'll continue on. Okay, and the drag force is getting to be 0 now. Why? Because the object is slowing right down. It's reaching the top of its shot here. And then when it stopped, there's no more drag force, or very little drag force. So this is the top of the projectile path. Okay, because it was fired really fast, but there was huge, it's just like throwing up a piece of paper. It doesn't go very far unless you start crumpling it. Now it's coming back down, and as you notice, the force of gravity is still constant. It's now getting speed downward, but this drag force is in the opposite direction of the speed. And this drag force is going to get bigger. But as it gets bigger, you see that it can't and will not go above and bigger than this force of gravity. It'll only match that force of gravity. And once it matches that force of gravity, you'll see that the distance between the dots are the same. And this is what's called terminal velocity. Let's just zoom in there. And as we go down, the force is not changing, the drag force and the force of gravity are the same, and it's the same distance all the way along. So it falls at a constant speed, and that's called the terminal velocity. Okay. So we're coming up now to Newton's 3 laws of motion. Newton's 3 laws of motion. One is called the law of inertia, one is called the law of acceleration, and the other is called the law of action-reaction. So, at this point, I'm going to wind up this video and continue on with the Newton's 3 laws of motion in their next short video. Thank you for watching. I know it's tough, there's a lot of terminology here, and just had to get through it. And hey, no calculations yet. For those people that hate math, oh, I pity you. I'm sorry for you. I love math. Anyhow, miss you guys. Take care. Enjoy. Subscribe. Like. Comment. Here comes the jingle.